Tonight, we journey toward the edge of the invisible, to the event horizon, a border where the very laws of reality begin to fade. Once seen only as a symbol of absolute destruction, it reveals a profound, cosmic stillness, a place where time and light reach their ultimate end, and existence finds its quietest state. Welcome to the Orbit for Sleep channel. Here, science moves slowly, quietly, and without urgency. Let us follow the orbit of science and drift gently towards sleep. You find yourself traveling through a vast, silent expanse of the cosmos. Far from the glowing nebulae and crowded star clusters, you approach a region where the very fabric of existence begins to change. Ahead, a perfect sphere of absolute darkness rests against the backdrop of distant stars. This is the edge of a black hole, a place where the universe as we understand it reaches its limit. The light from distant galaxies behind this dark sphere does not move in straight lines. Instead, you notice the starlight curving and stretching into long, brilliant arcs, creating a halo of captured photons. This visual distortion is the first sign that you are entering a realm dominated by extreme gravity. In the early 20th century, specifically in 1915, Albert Einstein shifted our understanding of the universe by suggesting that space and time are not separate. They form a single, flexible fabric called space-time. A black hole is a point where this fabric is warped so deeply that it creates a bottomless well. As you move closer to the boundary known as the event horizon, the physical laws that govern your daily life begin to fade. You observe that the passage of time is no longer a constant. Gravity is so powerful here that it physically stretches time itself. To understand this phenomenon, you might think of a wide, calm river flowing toward a massive waterfall. Far upstream, a boat moves freely in any direction. However, as the boat nears the edge of the falls, the current grows stronger. There is a precise line where the water moves faster than any engine can push back. Once the boat crosses that line, the descent becomes inevitable. The event horizon is that invisible line in space. It is the mathematical and physical point where the escape velocity required to leave exceeds the speed of light. Since nothing in the universe travels faster than light, nothing that crosses this threshold can ever return to the outside world. In 1916, Carl Schwarzschild was the first to calculate the exact size of this boundary for a non-rotating mass. He discovered that every object, if compressed enough, has a radius where it would become a black hole. For our Sun, this radius is only about 3 kilometers. For the Earth, it is less than 9 millimeters. This scale reveals the incredible density required to create such a fold in the universe. As you hover just outside this limit, you notice a profound silence. The light from the outside world is still visible, but it appears shifted in color, becoming deeper and redder. At this border, the concept of now begins to lose its meaning. If an observer far away were watching you, they would notice your movements slowing down more and more as you approach the horizon. To them, you would seem to freeze at the edge, becoming a permanent, motionless silhouette against the darkness. You realize that the event horizon is not just a place in space, but a boundary in time. It represents the ultimate frontier of human knowledge, a threshold where the known laws of physics meet the unknown. You remain at this peaceful, silent edge, observing the magnificent stillness of a place where time, for all practical purposes, has come to a stop. The term event horizon refers to a boundary in space-time that acts as a one-way membrane. You observe that this is not a solid barrier or a visible wall, but a threshold of pure gravity. Once an object or even a single particle of light crosses this line, the path leading back to the outside universe ceases to exist. In the 20th century, specifically in 1916, the German physicist Carl Schwarzschild provided the first mathematical description of this limit. He calculated that for any given mass, there is a specific radius where the escape velocity required to leave exceeds the speed of light. This distance from the center of a black hole is now called the Schwarzschild radius. To understand the nature of this boundary, you can look at the concept of escape velocity on Earth. When a rocket attempts to leave our planet, it must reach a speed of about 11 kilometers per second to overcome Earth's gravitational pull. If the rocket is slower, it eventually falls back. However, a black hole is so dense that it concentrates an enormous amount of mass into an incredibly small volume. As you move closer to its center, the required escape velocity increases steadily. At the event horizon, that required speed reaches 300,000 kilometers per second, which is the speed of light. Because the universe does not allow anything to travel faster than light, the event horizon becomes an absolute point of no return. You notice that the event horizon is essentially a shadow of the laws of physics. It defines a region where the future of every object points in only one direction, toward the singularity at the center. You might imagine a person walking on a moving walkway that is traveling faster than they can run in the opposite direction. No matter how much effort they exert, they are carried toward the end of the path. In the same way, once space-time is curved so severely at the horizon, the geometry of the universe itself forces all paths inward. There is no physical force that can push back against this curvature. The scale of these horizons varies immensely across the cosmos. If our sun were to become a black hole, its event horizon would be a sphere with a radius of only 3 kilometers. If the entire Earth were compressed into such a state, the horizon would be no larger than a small marble, roughly 9 millimeters in diameter. In contrast, supermassive black holes at the centers of galaxies, like the one in M87, photographed in 2019, have event horizons that are billions of kilometers wide, spanning areas larger than our entire solar system. You recognize that despite these vast differences in size, the fundamental rule remains the same. The horizon is a silent, invisible gate that opens only inward, marking the definitive edge of the observable world. The universe operates under a strict cosmic speed limit. Light travels at approximately 299,792 kilometers per second, a velocity that remains constant for all observers. In our daily experience, light seems to move in perfectly straight lines, illuminating the world instantly. You might notice how a beam from a flashlight appears to travel forever into the night. However, Albert Einstein demonstrated in 1915 that gravity is not merely a force pulling on objects with mass, but a curvature of space-time itself. Because light exists within space-time, it must follow the curves and dips created by massive objects. To visualize this interaction, you can consider the behavior of a ball thrown into the air on Earth. If you toss it gently, the planet's gravity pulls it back down almost immediately. If you could throw it with significantly more force, it would reach a higher altitude before falling. To leave Earth entirely, an object must reach the escape velocity of 11 kilometers per second. Now, you might extend this logic to a black hole. As a star collapses into an extremely dense state, its gravitational pull becomes so intense that the curvature of space-time becomes nearly vertical. Historically, the idea of an object so dense that light could not escape was first proposed in 1783 by John Michell. He used the term dark stars to describe these theoretical bodies. By the 20th century, modern physics confirmed that as the escape velocity of a collapsing star reaches the speed of light, a unique physical barrier is formed. This is the event horizon. At this specific distance, the tilt of space-time becomes so extreme that all possible paths for light are bent back toward the center. Even if a flashlight is pointed directly away from the black hole, the photons are forced to curve inward by the sheer geometry of the environment. The reason nothing can escape is found in the fundamental structure of the universe. In normal space, your future paths are wide and varied, allowing you to move in any direction. However, inside the boundary of the event horizon, space-time is warped to such a degree that every possible direction leads toward the singularity. You find that the outward direction no longer exists in a physical sense. Just as you cannot move backward into yesterday, a particle inside the horizon cannot move toward the outside universe. Gravity does not just pull the light, it swallows the very paths that light would use to flee. This creates a region of absolute isolation, where the fastest entity in the cosmos is held stationary by the weight of space itself. Before the early 20th century, the scientific world viewed gravity as an invisible force that acted instantly between two objects. In 1915, Albert Einstein published his general theory of relativity, which completely redefined this concept. He proposed that the universe is not an empty stage, but a four-dimensional fabric known as space-time. In this view, gravity is not a pull, but a result of the fabric warping in the presence of mass and energy. This discovery shifted the focus from the objects themselves to the geometry of the space around them. To understand this curvature, you might consider a simple daily example. Envision a large, tightly stretched fabric, like a soft mattress or a trampoline. If you place a small marble on it, the surface remains nearly flat. However, if you place a heavy lead ball in the center, the fabric curves downward, creating a deep depression. If you then roll the smaller marble near the lead ball, it does not move in a straight line. Instead, it follows the curve of the fabric, circling the heavier object. Einstein realized that planets, stars, and even light behave exactly like that marble, following the unseen contours of the universe. The most extreme consequence of this theory was the prediction of a point where the curvature becomes infinite. Einstein's field equations suggested that if enough mass is concentrated into a small enough space, the resulting hole in space-time would be so deep that nothing could ever climb out. In 1916, while serving on the front lines of the First World War, Karl Schwarzschild used Einstein's equations to provide the first exact solution that described such a region. Although the term black hole was not used until much later in the 20th century, the mathematical foundation for its existence was firmly established during this period. One of the most remarkable aspects of this vision is that it allows us to see the invisible. Even though a black hole emits no light, its effect on the surrounding space-time is profound. In 1919, a solar eclipse provided the first physical proof of Einstein's theory. Astronomers observed that the light from distant stars shifted slightly as it passed near the sun, confirming that gravity indeed bends light. This phenomenon, known as gravitational lensing, acts like a cosmic magnifying glass. On a much larger scale, this effect allows modern telescopes to detect the presence of black holes by observing how they distort the light from galaxies located far behind them. You recognize that through the lens of general relativity, the dark and silent voids of the cosmos become readable structures that define the very shape of our universe. In April 2019, a historic milestone was reached in our exploration of the cosmos. For the first time, humanity captured a direct image of a black hole's immediate surroundings. This image features a dark, circular center framed by a glowing, irregular ring of orange and yellow light. You notice that the center is not merely an absence of light, but a physical silhouette known as the black hole's shadow. This shadow is approximately 2.5 times larger than the event horizon itself, caused by the extreme bending of light as it attempts to pass near the massive object. The subject of this observation is the supermassive black hole at the center of the Messier 87 galaxy, located 55 million light-years away. To capture such a distant object, scientists in the 21st century coordinated a global network of 8 ground-based radio telescopes. This project, known as the Event Horizon Telescope, synchronized data from locations ranging from the high deserts of Chile to the frozen expanse of the South Pole. By combining these signals, they created a virtual telescope the size of the entire Earth, providing the resolution necessary to see an object that appears as small as a pebble on the moon. To understand why the ring is visible, you can imagine a dark sphere placed in front of a bright, glowing lamp. Even if the sphere is perfectly black, you see its shape because it blocks the light behind it and creates a sharp outline. In space, the glowing ring is formed by the accretion disk, a whirlpool of superheated gas and dust, swirling toward the event horizon at nearly the speed of light. You observe that one side of the ring appears brighter than the other. This is a natural phenomenon caused by the rotation of the gas. The light moving toward your perspective is intensified, while the light moving away grows dimmer. The scale of M87 times is difficult for the human mind to fully grasp. It contains the mass of 6.5 billion suns. Its event horizon is so large that it could easily contain our entire solar system, with room to spare. The 2019 image confirmed decades of theoretical work, proving that the shadows predicted by Einstein's equations are a physical reality. As you observe this distant, glowing ring, you realize that you are looking at the interface between the known universe and a place where information is lost forever. The image serves as a silent testament to human curiosity and the ability to visualize the most hidden corners of the vast, dark cosmos. As an object approaches a black hole, it encounters a physical process known as spaghettification, or the tidal effect. This phenomenon occurs because of the extreme gradient in gravitational strength over a very short distance. You notice that the gravitational pull on the side of an object closest to the black hole is significantly stronger than the pull on the side further away. In the 20th century, specifically in 1988, physicist Stephen Hawking popularized this term to describe the fate of any matter venturing too close to a stellar mass black hole. To understand this stretching, you might consider a simple daily example using a common rubber band. When you hold both ends and pull them in opposite directions, the band grows longer and thinner. In the vicinity of a black hole, gravity performs a similar action on a molecular level. If a person were to fall toward a black hole feet first, the gravity acting on their feet would be vastly more powerful than the gravity acting on their head. This difference, known as a tidal force, creates a vertical tension that stretches the body while simultaneously compressing it horizontally. Every atom within the object is forced into a long, thin strand resembling a piece of noodle. The history of this concept is tied to our understanding of tides on Earth. The moon's gravity pulls on Earth's oceans, creating a slight bulge. However, because a black hole is millions of times denser than the moon, these tidal forces become destructive rather than gentle. You observe that the intensity of spaghettification depends entirely on the mass of the black hole. Paradoxically, this effect is much more violent near smaller, stellar mass black holes. Because their event horizons are so close to their centers, the change in gravity over a small distance is incredibly sharp. An object would be torn apart long before it even reached the horizon. In contrast, the scale of supermassive black holes offers a different experience. Because their mass is spread over a much larger volume, the tidal forces at the event horizon are surprisingly weak. One might pass through the boundary of a supermassive black hole without feeling any immediate physical discomfort. The stretching would only begin much later, as the object travels deeper toward the central singularity. You realize that this process is a testament to the absolute power of gravity to reshape the physical form of matter. It is a silent, inevitable transformation where the structures of the material world are refined into their most basic, elongated states. In the early 20th century, specifically in 1915, Albert Einstein introduced a concept that fundamentally changed our perception of time. He proposed that time is not a universal constant that flows at the same rate everywhere. Instead, time is a dimension woven into the fabric of space, and it is subject to the influence of gravity. You notice that the stronger the gravitational field, the slower time passes relative to an observer in a weaker field. This phenomenon is known as gravitational time dilation, and it has been verified through precise experiments over the last century. To observe this effect in a daily context, you can look at the Global Positioning System, or GPS, satellites orbiting Earth. Because these satellites are farther away from Earth's mass, they experience slightly weaker gravity than we do on the surface. Consequently, their atomic clocks run approximately 45 microseconds faster every day. If scientists did not adjust for this tiny difference, GPS navigation would become inaccurate within hours. While this change is nearly imperceptible to humans, it proves that time is physically flexible. As you move from the scale of a planet to the scale of a black hole, this effect becomes extreme. Near the event horizon, the curvature of space-time is so profound that the passage of time slows down to an extraordinary degree. You might imagine an observer watching from a safe distance as a probe descends toward a black hole. To the distant observer, the probe appears to move slower and slower as it approaches the horizon. The light signals from the probe become stretched and reddened, and the clock on the probe seems to eventually freeze entirely. To the outside world, the probe remains suspended at the edge of the void for an eternity. However, From the perspective of someone traveling with the probe, time feels as though it is passing normally. You notice a strange contrast. While your own clock ticks steadily, the rest of the universe outside the black hole appears to accelerate. You observe stars flickering and dying in what seems like seconds, and the evolution of entire galaxies passing before your eyes. This happens because while your time is slowed by the intense gravity, the universe outside continues at its standard pace. You realize that at the very edge of the horizon, a single second of your experience could correspond to thousands of years in the distant cosmos. This silence and stillness represent the ultimate stretching of the present moment, where the boundaries of now expand to encompass the history of the universe. While the interior of a black hole is a realm of absolute darkness, the area immediately surrounding it is often one of the brightest places in the universe. This radiant structure is known as the accretion disk. It is a rotating disk of gas, dust, and stellar debris that has been captured by the black hole's immense gravity. As this matter spirals inward, it does not fall straight down. Instead, it orbits the center at incredible speeds, often approaching a significant fraction of the speed of light. You notice that the motion of this material creates a glowing halo that illuminates the void. To understand why this disk glows so intensely, you can think of a common daily occurrence. When you rub your hands together quickly on a cold day, the friction generates heat. In the accretion disk, the particles of gas and plasma are moving so fast that they constantly collide and rub against one another. This extreme friction generates temperatures reaching millions of degrees Celsius. At such high energy levels, the disk emits vast amounts of radiation, ranging from visible light to high-energy X-rays. What you observe is the conversion of gravitational energy into pure, brilliant light. The scientific understanding of these disks reached a milestone in 1973, when physicists Nikolai Shakura and Rashid Sunyaev developed the standard model for how matter behaves as it spirals into a massive object. Their work explained how the viscosity within the disk allows matter to lose angular momentum and gradually move closer to the event horizon. You recognize that this process is similar to water swirling around a bathtub drain. The water moves faster as it nears the center, creating a vortex. In space, this vortex is composed of superheated plasma that can span distances much larger than our entire solar system. The light from these disks often travels across the vastness of space for millions or even billions of years before reaching our telescopes. When you look at an image of a distant quasar or the glowing ring of M87, you are witnessing ancient history. The photons that enter the camera today began their journey when the Earth looked very different, or perhaps before humans existed. This light carries information about the environment near the black hole, revealing the speed of its rotation and the density of the surrounding matter. You find peace in the realization that this ancient glow serves as a bridge across time, connecting the modern world to the most energetic events in the deep past of our universe. As you venture deeper into the gravitational well of a black hole, you encounter a region even more surreal than the glowing accretion disk. This is the photon sphere, a theoretical boundary located just outside the event horizon. At this precise distance, gravity is so intense that photons, the fundamental particles of light, are forced to travel in perfect circles. You notice that in this region, light does not simply pass by or fall in. It orbits the black hole, much like a planet orbits a star. For a non-rotating black hole, this sphere exists at exactly 1.5 times the distance of the Schwarzschild radius. To understand this phenomenon, you might consider the behavior of a satellite in orbit around Earth. A satellite stays at a constant altitude because its forward velocity balances the planet's gravitational pull. In our daily lives, light travels too fast for Earth's gravity to bend it into a circle. However, near a black hole, the curvature of space-time becomes so extreme that even the fastest entity in the universe is captured. You observe a silent, invisible ring, where light from distant stars is trapped in a perpetual loop, circling the darkness over and over again. The mathematical foundation for the photon sphere was established in the 20th century, following Albert Einstein's publication of general relativity in 1915. Physicists realized that if light follows the curvature of space, there must be a point where that curvature forms a closed loop. Historically, this area was of great interest because it represents the last place where light can still escape to the outside world. The photon sphere is inherently unstable. A photon slightly nudged inward will fall into the event horizon, while one nudged outward will eventually fly away into space. It is a precarious balance at the edge of the abyss. If you were to hover at this exact location, you would experience a visual reality unlike any other. Because light orbits in a circle, the photons reflecting off the back of your head would travel all the way around the black hole and return to your eyes. You would notice your own image appearing in front of you, wrapping around the sphere of darkness. This region defines the inner limit of the glowing rings we see in telescopic images. You recognize that the photon sphere is a place of profound stillness and paradox, where the fastest moving energy in nature is held in a silent, eternal embrace by the geometry of the void. For decades, the scientific community believed that black holes were cosmic dead ends from which nothing, not even a single subatomic particle, could ever escape. However, in 1974, the British physicist Stephen Hawking introduced a theoretical discovery that bridged the gap between general relativity and quantum mechanics. He proposed that black holes are not perfectly black, but instead emit a faint glow of energy, now known as Hawking radiation. This process suggests that black holes have a temperature and, over an immense period of time, they may eventually lose mass and evaporate entirely. To understand how a black hole can lose mass, you look at the nature of the vacuum in space. On a quantum level, a vacuum is not truly empty. It is a sea of activity where pairs of virtual particles, a particle and an antiparticle, constantly pop into existence and immediately annihilate each other. You observe this cycle happening everywhere in the universe. However, when these pairs appear exactly at the boundary of the event horizon, a unique event occurs. Before they can annihilate, one particle falls into the black hole, while the other escapes into space as radiation. Because the law of conservation of energy must be maintained, the particle that falls into the black hole is considered to have negative energy relative to the outside world. You notice that every time this happens, the black hole loses a tiny fraction of its mass to compensate for the particle that escaped. You might compare this to the slow evaporation of a puddle of water on a cool day. Even without direct sunlight, the most energetic molecules at the surface gradually escape into the air, causing the puddle to shrink over time. In the cosmos, Hawking radiation acts as this slow, invisible evaporation. The scale of this process is incredibly slow for the black holes we observe today. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate, a duration much longer than the current age of the universe. However, as a black hole grows smaller, its temperature increases, and the rate of evaporation accelerates. In the final moments of its existence, a black hole would release its remaining energy in a massive burst of gamma rays. You recognize that through Hawking radiation, the universe maintains a balance where even the most permanent structures are subject to the passage of time. This realization brings a sense of profound quiet as it reveals a universe where everything, even the giants of the dark, eventually returns its energy to the vastness of space. You imagine a journey deep into the center of our home galaxy, the Milky Way. Leaving behind the familiar spiral arms and the light of distant suns, you move toward a region where the density of stars increases dramatically. At the very heart of this celestial metropolis lies a silent, invisible gravitational anchor known as Sagittarius A*. While most black holes form from the collapse of a single star, this supermassive black hole contains the mass of 4 million suns. It serves as the gravitational pivot around which our entire galaxy rotates, holding billions of stars in a stable, eternal dance. The discovery of this central mystery began in 1974, when radio astronomers detected a strong, compact source of radio waves coming from the galactic center. In the late 20th century, specifically starting in the 1990 seconds, Scientists used infrared telescopes to peer through the thick clouds of cosmic dust that obscure the heart of the Milky Way. You observe the results of their decades-long study. A group of massive stars orbiting a seemingly empty point at incredible speeds. In 2020, the scientific community recognized this achievement, confirming that only a supermassive black hole could exert such a profound influence on these stars without emitting any visible light of its own. To understand the role of Sagittarius A*, you might consider the mechanism of a carousel in a park. The colorful horses and the platform move in a circle because they are tethered to a heavy, stationary central pillar. Without this anchor, the centrifugal force would cause the structure to fly apart. In the cosmos, Sagittarius A* acts as that central pillar. Its presence regulates the orbits of stars in the galactic nucleus and influences the overall structure of the Milky Way. Although it is 26,000 light-years away from Earth, its gravitational signature is the reason our galactic neighborhood remains a cohesive and organized system. The scale of Sagittarius A* is a study in density. Despite its enormous mass, its physical size is relatively small. Its event horizon would fit comfortably within the orbit of the planet Mercury. You notice the contrast between its compact size and its vast authority over the surrounding space. Unlike some active galaxies where the central black hole consumes matter violently, our local giant is currently in a quiet, dormant state. It sits in the darkness, a silent guardian that has overseen the evolution of our galaxy for billions of years. You find a sense of security in this cosmic order, realizing that the stability of our stellar home is anchored by this profound, unseen force at its core. Every object in the universe, from a distant star to a single grain of sand on Earth, carries a unique set of data. In the world of quantum mechanics, this is known as information, the specific arrangement of atoms and energy that defines what an object is and what its history has been. According to the fundamental laws of physics established in the 20th century, this information can never be truly destroyed. Even if you were to burn a handwritten letter, the information contained in the words is technically still present in the specific patterns of smoke, ash, and heat. In theory, if you had a powerful enough computer, you could reconstruct the original letter from these fragments. However, the existence of black holes creates a profound conflict known as the information paradox. In 1974, Stephen Hawking demonstrated that black holes eventually evaporate through Hawking radiation. The problem arises because this radiation appears to be completely thermal and random, carrying no trace of what the black hole once consumed. If a book falls into a black hole and the black hole eventually disappears, it seems as though the information within that book is deleted from the universe forever. This would mean that the laws of quantum mechanics are broken, creating a gap in our understanding of how reality operates. To visualize this paradox, you might consider a digital file stored on a hard drive. In our daily lives, if you delete a file, the magnetic traces often remain on the disk until they are overwritten. But imagine a shredder that not only cuts the paper into pieces, but erases the very existence of the ink and the fibers themselves. You realize that if black holes truly destroy information, the past becomes unreachable and the future becomes unpredictable. The history of every atom that ever entered the event horizon would be scrubbed from the cosmic record. In the late 20th century, specifically during the 1990 seconds, physicists like Leonard Susskind proposed a potential solution called the holographic principle. They suggested that when an object falls into a black hole, the information is not lost inside, but rather smeared onto the two-dimensional surface of the event horizon. You might think of this like a 3D hologram on a flat credit card. All the depth and detail of the original object are encoded on the surface. As the black hole evaporates, this information is slowly leaked back into the universe through the radiation. While the debate continues in the 21st century, you recognize that this paradox forces us to reconsider the very nature of reality. It suggests that the universe might be a giant storage system where every moment of history is preserved, even at the edge of the deepest darkness. When you look at a galaxy, you see a vast ecosystem where stars are born, live, and eventually fade away. In the center of this system, the supermassive black hole plays a role far more complex than simple destruction. It acts as a regulator of the galaxy's growth. You observe that as matter falls toward the event horizon, not all of it is consumed. Instead, a significant portion of the energy is redirected outward in the form of massive jets of plasma and radiation. This process is known as black hole feedback, and it is a fundamental mechanism that shapes the evolution of the cosmos. To understand this regulatory role, you might consider a gardener tending to a large garden. If a gardener never prunes the plants, the garden becomes overgrown, and smaller plants may die from a lack of sunlight. Conversely, if the gardener provides the right amount of water and clears away excess growth, the entire ecosystem flourishes. In a galaxy, if too many stars form too quickly, they exhaust the available gas and the galaxy dies prematurely. The energy released by the central black hole heats the surrounding gas, preventing it from cooling and collapsing into new stars too rapidly. You notice that this maintains a balanced rate of star formation over billions of years. The discovery of this connection began in the 20th century, specifically in 1963, when astronomer Martin Schmidt identified the first quasar. Quasars are incredibly bright centers of distant galaxies powered by supermassive black holes. Scientists realized that the immense energy from these quasars could push away vast clouds of cold gas, the raw material for stars. While this can stop star formation in some areas, the pressure from these cosmic winds can also compress gas clouds in other regions, triggering the birth of thousands of new suns. You find that the black hole is simultaneously a brake and an engine for the galaxy's life cycle. On a cosmic scale, this feedback loop explains why galaxies come in specific shapes and sizes. Without the influence of the central black hole, galaxies would look much different and might not have the stability required to support long-lived stars like our Sunday. You observe a delicate balance where the most violent objects in the universe create the very conditions necessary for a quiet, stable environment. This realization reveals a universe that is deeply interconnected, where the darkness at the center of a galaxy serves as the invisible hand that nurtures the light of the stars. You remain in this state of peaceful observation, recognizing the orderly patterns within the vast, silent garden of the night sky. The human brain is a product of millions of years of evolution on a specific, manageable scale. It developed to navigate a world defined by the length of a day, the distance a person can walk, and the objects they can touch. This biological history has created a sensory system that is highly efficient at processing immediate surroundings, but struggles when faced with the infinite dimensions of the cosmos. You observe that when you think about the event horizon of a black hole, or the billions of years it takes for one to evaporate, your mind reaches a boundary where logic meets a sense of profound stillness. To understand this cognitive limit, you might consider a daily example of numerical perception. Human beings are naturally skilled at recognizing small quantities instantly. If you see 3 apples on a table, your brain identifies the number without needing to count them. However, as the numbers increase to thousands or millions, the brain begins to treat them as an abstract category labeled many. In the 20th century, specifically through the study of evolutionary psychology, researchers found that our ancestors did not require an intuitive grasp of the distance to the stars for survival. Consequently, when you hear that a black hole is 55 million light-years away, the brain translates this vast distance into a feeling of immense space rather than a precise measurement. The history of our expanding perception began to shift significantly in 1924, when astronomer Edwin Hubble proved that the Milky Way was only one of many galaxies. This discovery forced humanity to confront a universe that was much larger than previously imagined. You notice that the brain often uses analogies to bridge the gap between the human scale and the cosmic scale. For instance, if you were to represent the entire history of the universe as a single year, the total duration of human civilization would occupy only the final few seconds of December 31st. This mental mapping is a tool the mind uses to prevent itself from being overwhelmed by the sheer magnitude of time. This struggle with the infinite is not a flaw, but a characteristic of our physical existence. You recognize that the awe you feel when looking at a black hole is actually a neurological response to a stimulus that exceeds your brain's processing capacity. As you observe the dark, silent boundaries of the event horizon, you find that the inability to fully comprehend the scale allows for a state of mental relaxation. You are no longer required to measure or analyze. Instead, you accept your place within a vast, orderly system that exists far beyond the reach of human calculation. This state of quiet acceptance leads to a deep sense of peace as you surrender to the magnificent and silent reality of the infinite universe. Observing a black hole from Earth is a challenge that exceeds the capacity of any single instrument. Because these objects are both dark and located at vast distances, they appear incredibly small in the night sky. To capture the supermassive black hole at the center of the M87 galaxy, astronomers required a telescope with a resolution so sharp that it could read a newspaper in New York from a sidewalk cafe in Paris. In the 21st century, this feat was accomplished not by building a larger machine, but by transforming our entire planet into a single, synchronized lens. This project is known as the Event Horizon Telescope, or EHT. It is a global collaboration that began to take shape in the early 21st century, involving over 300 researchers and numerous institutions across the world. You notice that instead of a single mirror, the EHT uses a technique called very long baseline interferometry. This method allows multiple radio telescopes, separated by thousands of kilometers, to work together as a single virtual dish. In 2019, the EHT successfully revealed the first image of a black hole, followed by the image of our own galactic center, Sagittarius A*, in 2022. To understand how this collaboration works, you might imagine a giant mirror that has been shattered into many pieces, with those fragments scattered across different continents. Each piece by itself provides only a small, blurry reflection. However, if you could perfectly align all the fragments and combine their light, they would function as if they were still part of the original, massive mirror. The EHT operates on this principle. Telescopes in Hawaii, Chile, Mexico, Spain, and even the South Pole recorded data simultaneously, guided by atomic clocks so precise that they lose only 1 second every 100 million years. The scale of this effort involves moving vast amounts of data. During the observation campaigns, each telescope site recorded so much information that it could not be sent over the internet. Instead, hundreds of hard drives were physically flown to central processing facilities in the United States and Germany. You observe a unique moment in human history where the boundaries of nations and languages were set aside to solve a cosmic mystery. This global lens allowed us to see past the limits of our individual senses. You recognize that the image of the black hole is a silent monument to what humanity can achieve when it acts as a single, unified observer. This realization brings a deep sense of calm, knowing that we possess the collective wisdom to illuminate the darkest corners of the universe. The current age of the universe is defined by the light of stars. This period, known to cosmologists as the Stelliferous era, is a time of vibrant energy and constant creation. However, as the cosmos continues to expand, the raw materials for new stars will eventually be exhausted. One might look at the far future of the universe and see a transition into a much longer and quieter period. In 1997, astrophysicists Fred Adams and Gregory Laughlin described this future as the black hole era. This stage begins approximately 1 quadrillion years from now, long after the last red dwarf star has cooled and faded into darkness. To understand this transition, one might consider the life cycle of a large city at night. During the evening, the streets are illuminated by thousands of individual lights from homes and vehicles. As the night progresses toward dawn, these lights go out one by one. Eventually, only the massive, permanent stone structures of the city remain, invisible in the dark but still possessing immense mass. In the universe, black holes are these permanent structures. Once the stars are gone, the only remaining concentrations of matter will be the white dwarfs, neutron stars, and the black holes that have grown by consuming them. During the black hole era, the universe becomes a place of profound stillness and extreme cold. The primary occupants of the cosmos are supermassive black holes, which continue to exert their gravitational influence over the remnants of dead galaxies. You notice that even without the light of suns, the universe maintains a structural order. These giants will occasionally collide and merge, releasing massive ripples in space-time known as gravitational waves. These events are the final major physical interactions in a universe that has otherwise reached a state of maximum entropy. The scale of this era is nearly impossible to measure by human standards. While the age of stars lasts for only trillions of years, the black hole era is expected to continue for 1 Google years. Throughout this unimaginably long duration, the only active process is the slow, silent evaporation of black holes through Hawking radiation. One realizes that the universe is not heading toward a chaotic end, but toward a state of absolute equilibrium. As the final black holes eventually disappear into a faint mist of subatomic particles, the universe reaches its final state of rest. This vision of the far future provides a sense of ultimate quiet, where the activity of the present is replaced by a magnificent and eternal peace. The journey into a black hole ends at a point called the singularity, where the laws of physics, as we know them, cease to function. However, the mathematical frameworks of general relativity suggest that this may not be a simple dead end. In 1935, Albert Einstein and Nathan Rosen discovered a theoretical solution within the equations that described a bridge connecting two distant points in spacetime. This structure, known as an Einstein-Rosen bridge or a wormhole, presents the possibility that the interior of a black hole could lead to another location in our universe or even to a different dimension entirely. To understand this concept of a cosmic shortcut, you might consider a daily experience with a large building. If you wish to travel from the ground floor to the roof, you would typically use the stairs, passing through every floor in sequence. However, an elevator acts as a direct link that moves you between these 2 points without requiring you to traverse the space in between. In the geometry of the cosmos, a wormhole functions like that elevator. It creates a fold in the fabric of space-time, allowing for the possibility of a transition between regions that are otherwise separated by millions of light years. Throughout the 20th century, physicists expanded on these ideas, exploring the concept of white holes. A white hole is theorized as the mathematical opposite of a black hole. While a black hole only allows matter to enter, a white hole would only allow matter and light to exit. You notice a symmetry in this vision, where the matter swallowed by a black hole in one region of the cosmos might emerge from a white hole in another. While no white hole has been observed in the 21st century, the logic of general relativity remains open to their existence as part of a larger, interconnected multiverse. The scale of these extra dimensions is often described in modern string theory, which suggests that our universe may have more than the 4 dimensions we perceive. You recognize that the singularity within a black hole might be the point where our 3-dimensional reality meets these higher planes. This transition represents a shift in the very structure of existence. You observe this possibility with a sense of quiet curiosity, acknowledging that the most isolated places in the universe might actually be the most connected. This perspective transforms the dark void into a potential gateway, leading the mind into a state of peaceful contemplation about the vast and hidden architecture of the cosmos. The universe contains black holes in a staggering range of sizes, from microscopic points to giants that define the boundaries of galaxies. In the 20th century, specifically in 1974, Stephen Hawking proposed the existence of primordial or micro-black holes. These theoretical objects may have formed during the high-pressure environment of the Big Bang. While they could have the mass of a massive mountain, their physical size would be smaller than a single atomic nucleus. You observe that in the quantum realm, gravity and scale behave in ways that challenge our standard perception of matter. To understand the vast differences in these scales, you might consider a daily example involving a simple marble. If a micro-black hole is represented by a speck of dust, a stellar mass black hole formed from the collapse of a single star would be the size of a large city. These stellar mass black holes were first identified in the 20th century, with Cygnus X1 being a primary example confirmed in 1971. They typically contain between 5 and several dozen times the mass of our Sunday. You notice that even at this scale, the density is so extreme that a sphere only a few dozen kilometers wide can hold the entire weight of a star. As you move toward the centers of galaxies, the scale shifts from stellar to supermassive. Sagittarius A*, at the heart of the Milky Way, contains 4 million solar masses. However, even this giant is small compared to the largest known objects in the cosmos. In the 20th century, specifically in 1957, astronomers first identified an incredibly bright quasar known as TON 618. In the 21st century, it was confirmed to be powered by an ultramassive black hole with a mass of 66 billion suns. The event horizon of TON 618 is so vast that it could contain several solar systems arranged side by side. The scale of TON 618 represents the upper limit of what physics currently allows. You recognize that the light from its surrounding accretion disk is so powerful that it outshines all the stars in its host galaxy combined. If you were to compare our Sun to TON 618, it would be like comparing a single grain of sand to the entire Earth. You observe this magnificent spectrum of sizes with a sense of quiet wonder. From the invisible, subatomic points of the early universe to the multi-billion-ton anchors of space-time, each black hole maintains its place in the silent architecture of the cosmos. This realization leads to a state of profound calm as you accept your position within a universe that spans such incredible and orderly dimensions. The event horizon of a black hole serves as the ultimate physical boundary in the universe. It is a region where the laws of nature, as they are currently understood, reach a definitive limit. Within this boundary lies the singularity, a point where general relativity predicts infinite density and the breakdown of space-time. Throughout the 20th century, scientists struggled to reconcile this prediction with the laws of quantum mechanics. You observe that this physical edge is not just a place in space, but a profound metaphor for the limits of human knowledge and the boundary between what is observable and what remains forever hidden. To understand this metaphorical boundary, you might consider the daily experience of standing on a vast, flat beach and looking out at the ocean. No matter how high you stand, your vision ends at the horizon. You recognize that the ocean continues far beyond that line, but the curvature of the Earth prevents you from seeing it. The event horizon functions in a similar way. It represents the point where information, the very light that allows us to see, cannot return to us. You find that the universe contains regions that are fundamentally beyond the reach of human inquiry, regardless of the technology we possess. The history of this realization is tied to the development of modern physics. In 1915, Albert Einstein provided the equations that allowed us to predict the existence of these horizons. Later in the 20th century, the discovery of the cosmic microwave background radiation established another kind of horizon, the edge of the observable universe. You notice a recurring pattern, where the more humanity learns, the more clearly we define the boundaries of what we cannot know. The singularity inside a black hole is the most extreme example of this limit, a place where the mathematical language used to describe reality no longer provides answers. This encounter with the unknown is not a source of frustration, but a gateway to intellectual and physical stillness. You recognize that the existence of a horizon allows for a sense of privacy and mystery within the vast architecture of the cosmos. Just as the brain needs sleep to process the data of the day, the universe possesses regions where the noise of information is silenced. You observe the event horizon as a quiet reminder that it is not necessary to understand everything to exist within the system. This acceptance of the unknown leads to a state of profound relaxation. You surrender the need for certainty and embrace the calm, silent reality of a universe that preserves its deepest secrets behind a veil of gravity and time. The vast majority of the universe consists of empty space, a vacuum where the familiar sounds of the world are absent. In our daily environment, sound is a mechanical wave that travels through a medium, such as air or water. You notice the rustle of leaves or the hum of distant traffic because the atmosphere carries those vibrations to your ears. However, in the profound void surrounding a black hole, there is no air to vibrate and no medium to carry a pulse. This creates a state of absolute, eternal silence that defines the true nature of the cosmos. To understand this lack of sound, you might consider the experience of a professionally designed soundproof room. In such a space, every external noise is stripped away, leaving only the sound of your own breath and the steady rhythm of your heartbeat. Initially, the silence feels heavy, but as you remain still, your nervous system begins to relax, no longer needing to process constant auditory stimuli. The void of space offers this state on a cosmic scale. One observes that the regions between galaxies are so sparsely populated with atoms that even the most violent cosmic events, such as the birth of a star or the merging of black holes, occur in total, majestic silence. The scientific study of the vacuum began to take shape in the 17th century. In 1660, the chemist and physicist Robert Boyle performed an experiment with a bell inside a glass jar. As he pumped the air out of the jar, the sound of the bell grew fainter until it vanished completely, even though the clapper was still striking the metal. This provided the first physical proof that sound cannot exist without a medium. In the 20th century, modern astronomy confirmed that this silence extends across the billions of light years of the observable universe. You recognize that the black hole, the ultimate consumer of matter and light, is also the ultimate sanctuary of this stillness. The scale of this silence is a fundamental characteristic of the universe's architecture. While the Earth is a rare pocket of vibration and life, the cosmic norm is the quiet of the vacuum. This stillness is not an empty or negative state, but a manifestation of perfect equilibrium. In the vicinity of the event horizon, where time slows and the known world fades, the silence becomes even more profound. You observe that in this absolute stillness, the friction of existence disappears. You find that the void is a place of rest, where the energy of the universe is held in a state of eternal, motionless peace. You exist within this vast, quiet expanse, moving deeper into a state of total relaxation as you accept the magnificent and silent reality of the dark cosmos.